Welcome back to my channel. So we'll continue with how to ace your technical coding interview question. So the question we have before us is find eventual safe state. So here it says there's a directed graph of n nodes with each node labeled from 0 to n minus 1. The graph is represented by 0 index to the integer array graph, where graph I is an integer array of nodes adjacent to node I, meaning there's an edge from node I to each node in graph I. So a node is terminal node if there are no outgoing edges. A node is safe node if every possible path starting from that node leads to a terminal node and another safe node. Turn an array containing all the safe nodes of the graph. The answer should be stored in a scenario. So we have an example here. Graph which is 1 2 2 3 5 0 5, and so the output is 2 4 5 6. So the given graph is shown above. So we have nodes 5 and 6 are terminal nodes as there are no outgoing edges, so that one is clear. Every path starting at nodes 2 4 5 and 6 all lead to either node 5 or 6. Okay, what this question is essentially saying is that the output should give us what we refer to as a safe node, and a node is safe by definition if there are no outgoing edges. So 5 and 6 is clear. But another condition is that a node is also safe if, well, there could be outgoing edges, but eventually that outgoing edges leads to a terminal node. To put it another way, that outgoing edges does not result into a cycle, so it's coming alive now. So what it means is that find all the nodes where is either there are no outgoing edges or it does not end up in a cycle. So that's why 2 is involved, because it doesn't end up in a cycle. 4 is also involved because if you have an outgoing edge and you trace it, it doesn't end up in a cycle. But 0 is not involved because you could end up in a cycle. So 0 to 1, then to 2, and uh, you could actually get back to 0 and you could get back to 1. Okay, so why is 2 not involved? So let's no, not because of that. Sorry, I take that back. 0 is not involved because you could go from 0 to 1, not to 2 to 3, and you could go back to 0. Yeah, so 1 is not included because from 1 you could go to 3 and you could go back to 0 and you could go back to 1. 3 is not involved because from 3 you could go to 0, you could go to 1. So basically we're trying to dictate a cycle. So we have this constraint, the graph length, and the graph issue is sorted in increasing order, no self-loop. The number of edges in graph will be in this range. Okay, so value, the length could be 0, n is from 1 to this and this. So how do we approach this problem? This is a graph question. We are going to return a list. So now there's just no way we will know whether if we go through each of these. So this one represents node 0, everything, all the outgoing edges on node 0, so that's why we have 1 and 2. This represents node 1, the outgoing edges, that's why we have 2 and 3. So there's just no way for us to know whether we visit a particular node, whether it's going to end up, it's going to be a safe node. we can know that it's a terminal node if it's empty, like this, for 5 and for 6. So that's very easy. But we don't know whether it's going to be a safe node, if it will lead to a cycle. So we need to have a way of detecting a cycle. So that's one thing we should have at the back of our mind. So that means we're going to go to each of the nodes and we're going to try to detect a cycle. If we are unable to detect a cycle, that is when we can add the node to our result. So that gives us some idea. So we are returning a result which is a list, which is empty. At the end of everything we do, we're going to return that result. So in between, we need to populate the result with some values, with some nodes. Now, we need to go to each of the nodes. We have been told that our graph, the length of our graph cannot be 0. So at least we have at least 1 in the graph. Okay. So we don't have that base case. So what we can do is that we can now go through for nodes, each of the nodes in the graph. So we can say for so to be able to get the length, we need the length of the nodes. So the nodes is going to be the length of the graph. So that is how many nodes that we have. And let's see, it's 0 index, so that's good. So we have for 1, 2, 3, 4, 5, 6, 7. So 0 to 7. Okay, so we can now say for node in range of the nodes. So this will give us each of the 0, 1, 2, 3. So we can pick the first one, which is node 0. Now what we need to do is, can we add the first node 0 to a result? Not yet, we are not sure. So we can only add it if after we have gone through all its children. Okay, so what we can do is we need to get this node and go and try to find out if there is a cycle. So we will now say we need to detect cycle. Is cycle on this node? Is there a cycle? Either yes or no. Is cycle on this node? So we want to detect whether there is a cycle on that node, if it is true or false. So what we need to do then is if there is a cycle, we will not be able to add it. Okay, so if not cycle, because cycle will return true or false, then we can say result dot append that node, that current node. I think it's making some sense now. Okay, so we'll now define our cycle, which is like a DFS is cycle, and it's taking, shall we say n, let's use n as the current one node. For us to be able to know whether n, the current node, is a cycle or not, first of all we're going to do some finding validations. If at any point in time we discover that we get a cycle, so we return true. If at the end of the day we don't get a cycle, we're going to return false. So our default will be false. So in between that, we want to see whether we get a cycle and we can return true, that it results in a cycle. But how do we know if the node is going to end up in a cycle without keeping a visited node? So we need to have a dictionary that is going to help us to know whether we have visited the node before or not. So when this function n receives any new node, the first thing it wants to check is if that node is in visited. If it is in visited, then we can say that return whatever is in visited, whatever we have recorded in visited for this node. If it's a brand new node that this is not in visited, then we have to take an assumption. We have to first of all assume by adding it into the visited node and saying yes, we assume that it's going to return into a cycle. So we say it is true unless it is proven otherwise. So this is very important. We are assuming that any new nodes that we get must result into a cycle unless it is proven otherwise. So we assume that. Then we will now go through all its children of that particular node. So we say for children, because it's going to the out edges. So let's say it's the children in that particular node. So we are receiving n, so it will be, to get its children, to be grid of n. Then we're going to call cycle again, is cycle on that children, on each of those children. I can call it child. So let's use the child. Now, when we go through each of the child, if any of the child give us a true, that there is a cycle, then we will return true and break out of that loop. If we go through all the children and it did not return into, we were not able to enter into a true, then that means our assumption, which was initially true, becomes false. So we can say that assumption here, which we say it is true, we can immediately say no, our assumption for this particular n, which we say it is true, it must be a cycle, is wrong, then we can say false. This is a very programmatic way of see this concept, where you need to make an assumption, run some test, and if the test return true, then the assumption is never reached. But if you pass through the test, the entire for loop, and you couldn't find anything, then you can say, oh, our assumption is wrong. Then you bring it back to false. And I think that's it. So now what do you return for this particular n? You expect that if this doesn't give you a true all throughout, then you should have should return a false for this particular n. So it's either you return this false explicitly, or you can return whatever is in n here. Okay. So I would say, to be safe, we just return whatever is in n. And I think that should give us the same thing anyway. Well, that's it. It's a bit trickish. Recursive graph is a bit trickish to to go through, but once you practice it several times, uh, you can begin to see the same principle. So let's run it. We're supposed to dry run it, but it's not easy to dry run a recursion, so we just assume that should be correct. Let's see. Okay, so grid is not defined, so it should be graph. So let's graph. Sorry about that. So do we have graph anywhere else? What is that? So it's graph. So that's right. And let's see if it works. That works. So let's try the other one, second one too. Let's see if that works too. Copy is not correct. I didn't copy the first. This one. Okay, that works too. So let's try and submit and see if it passes all possible cases. Let's see that. Yeah, so that works too. So that's it. Just as a recap, the bottom thing there is first you have to go through each of the nodes, and that is what this is doing. And this is going to be in the 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 runtime complexity is going to be in the height of the graph, which is big of h, um, or big of log n, where n is the number of nodes. Okay, in the worst case. So um, so that's pretty it. And so this it's very important to go through each of the node, and then this detecting a cycle, and where you need to first of all be sure that whether you have it in a particular, you need to keep track of what you have visited or not, and you need to make an explicit assumption. And if your assumption it's if you go in there and say it's true, if it is not, then you have to change your assumption and return whatever you have there. Okay, all right, thank you very much, and see you in the next one.